sort of pick up where we left last time. So we were looking at BRDF models. Right? We were looking at BRDF functions last time. We looked at the general relationship that is expressed through a BRDF function in terms of the property between the radiance and the irradiance. Right? So now, what we want to start looking at is more specific models in terms of explanations or understanding of the different surface properties that are exhibited by objects. And the most common one, and of course the basic model that we always start off with, is a diffuse reflection model. So in general, of course, there are a variety of surface properties that are exhibited by objects. And when we look at an object, or for that matter, when you look at an image, just by looking at the intensity values in an image, you start at least getting a basic understanding of what the underlying surface property of that object might be. And the question is, how is it that we are able to infer those properties? And some of it has to go back and has to relate to how we believe the light reflects off of objects. Right? So there is obviously some model that we have in terms of the data that we are processing. So I get a bunch of intensity values that I'm looking at, and based on that I start making inferences on the properties, the surface properties of the object. The question is, what is the relationship that we are exploiting as part of our perception? And if we can understand those relationships, we can build models and thereby allow computers to make certain interpretations as well. So obviously when we look at a variety of objects, they exhibit, what we call semantic properties that we are capable of describing. Sometimes we may refer to an object as having a dull surface or a matte surface, right? More like a chalky substrate and so on and so forth. So these are typical expressions we use when we are trying to describe objects and surfaces that are more diffuse in their reflective properties. And what that really means is that the light reflected off of that surface is more or less uniform in all directions, almost independent of the source of illumination. So for example, if I look at the wall, right? I mean, in general, you see a pretty uniform distribution of intensity values on that wall. The question is, will the distribution of intensities dramatically change if I vary the illumination direction in this room, right? And yes, certainly it's going to change to a certain extent, but your inference in terms of the property of the object or the surface is not going to change dramatically because the reflection is still a more uniform reflection, and the change in the direction is not dramatically visible to us. Right? So how do we infer that? And diffuse reflection models allow us a basic interpretation of how that happens. Now also the reality is that in general, although we may want to think of everything in terms of a simplified model, incoming light falls on an object and reflects the light back, right? And we may try to relate that based on a basic BRDF function, right? So there's a factor, of course, in terms of saying that L, which is what I'm sensing, is some factor of the illumination on top of the object. Well, so that's a very, very generalized model. But we can start looking at the real aspects, the physical aspects of how light is interacting with matter. And besides reflection, there are many other phenomena going on. So truly, any surface that we look at the scale of a single photon or a ray of light, objects are not smooth. They have uneven surfaces at that scale. And most of the times we can describe surface properties in terms of microfacets, right? So there are uneven surfaces, and even though I may view this as a planar surface, the reality is there are many edges or grooves to it, and there's unevenness in terms of the planarity of the object. So it's natural to assume that incoming light is going to go through a variety of transformations, right? So some of the energy coming in is obviously going to get reflected. Some of the other energy coming in is probably going to get absorbed by the object. Portions of it is actually going to get reflected but may not actually transmit out of the object. It may simply scatter within the object because of the microfacets and the geometry of the underlying surface. Okay? So all of these things can happen. Now, for us, what we really care for is in simplified models, in sort of Lambertian type models that we can build. We don't really want to account for all these microfacets. We would rather try to simplify things and say, well, yeah, all of those are happening, but let's just say that all of the things that are non-reflective can be summed up as some scale factor of the total energy being projected onto the surface, right? So I will wrap around all the other effects and not really worry about them. They don't necessarily interfere with my ability to capture the reflected light off of that surface. Okay? So we can make those simplifications, and in those cases, our BRDF model essentially becomes a constant model. Okay? So what that means is that the amount of light going out is simply the amount of light coming in multiplied by some constant, preferably less than 1. So we can make our BRDF almost a constant model. And typically that's what we use in order to express diffused objects. Okay? So we can apply these models then and say, well, what can we interpret out of that? More importantly, yes, we try to do that in computer vision, but these have become also very nice, simple models to apply in graphics. Right? So if I want to render and try to give an impression of an object being diffused, we simply try to model it under a constant BRDF function. Now, from a vision standpoint, there are a couple other things that we actually care for in terms of measuring the surface properties of an object. One of them is what we call albedo. Okay? The albedo actually is what we really want to compute is a fraction of the incident irradiance that is reflected by the surface. Right? So as much as we want to think of the BRDF as a constant, the scale factor that we apply to this is really what we want to capture. Right? I want to know what that is, and that's what I will call the albedo of my object. Okay? So from a computational standpoint, vision standpoint, I want to know that. The other thing that we care about is radiosity. Right? Radiosity is nothing but the total power that leaves the surface per unit area, and that is computed regardless of the direction. I don't care which direction it's going in, but I want to know the total amount of radiosity of the object. So these are two properties that we do care for in terms of vision, and we'll come back to why we care about them. Okay. So generally now, if I take the simple models and apply them to objects, the first thing that we realize that we are expressing now the notion of radiosity, right? So what I really am interested in computing is the radiosity, the amount of energy that's actually being reflected or is going off of the object that I'm trying to image, right? Because that's actually what we are going to capture. So you can think of the reason to compute radiosity is because eventually you want to build a relationship between the intensity that you're observing with respect to the amount of energy that's leaving the surface. Because that energy is what we are capturing, right? Typically we are not capturing the source. We are actually observing objects in the 3D world. So it's that amount of energy that's getting projected onto the camera plane. So I want to capture that. But in measuring the radiosity, what I do care about is the albedo, right? So I need to know what the albedo is. So if I know somehow what is the amount of energy that actually is projected onto the object, then I will know how much of it is actually getting reflected. So the albedo tells me the fraction of the light that's actually going to be reflected off of that surface. I need to know that. And the other thing that I do need to know is, of course, the direction, if you will, in which that light is going to get transmitted. Okay? And the way we can measure direction is by actually looking at the normal of the surface that we have, or the object, and the angle that makes with respect to the direction of the light source. So I can express that in terms of a dot product where n is actually the normal to the surface, and s is actually the vector that points to the direction of the source. Now, of course, it's a vector, n being a normal, it's actually a unit normal, right? So it's really a magnitude of 1, but s has both a direction and a magnitude. So the amount of energy actually reflected off of the object is going to be given in terms of both the magnitude and the direction. So we can actually now compute radiosity based on this formulation, which is actually described under Lamb's law. And this holds true for all diffuse objects, where the radiosity that you're computing is actually normal times, or the dot product of the normal and the source vector multiplied by the albedo. Yeah. The radiosity, keep in mind, radiosity is actually independent of direction, because it is the cumulative value of the light being emitted per unit area. So it doesn't have a direction. So when you actually compute the dot product, you're getting rid of the directional component, but you are capturing the fraction, right? And then, of course, albedo tells you the amount